We're hosting tonight's webinar from the Astronomical Society of the Pacific in San Francisco, California. We're very excited to welcome our guest speaker, Dr. Michael Seiffert from NASA's Jet Propulsion Laboratory. Well, before we introduce Dr. Seiffert, here's Kat and Vivian, who I think are going to tag team a couple of announcements.
Hey, welcome everyone. I'll get you kicked off. For those of you joining us for the first time, and a big welcome. This is our monthly webinar series, and it's provided by the NASA Night Sky Network and the Astronomical Society of the Pacific. And here, NASA scientists share the latest updates from current missions and surveys. If you want to see some upcoming webinars, you can find those along with a treasure trove of past webinars on our YouTube page, which you're either already joining us from, or Kat's going to throw that link in the chat. Thank you, Kat. For those of you on Zoom, the Night Sky Network is a coalition of more than 400 astronomy clubs across the US. And if you're not already connected to your local club, you can find one close to you. And Kat's going to put that in the chat in YouTube. Kat, I think you have a couple more announcements too.
I certainly do. So for my coordinators that managed to add more than 10 events onto their club calendar by last week, be on the lookout for an email from me tomorrow by 3 p.m. Eastern, 12 p.m. Pacific. This is some really good news for you. It's an email you've all been looking forward to. In addition, we also are kicking off our Cosmic Conversations series again. This will happen on February 4th at 5 p.m. Pacific, 8 p.m. Eastern, where we will discuss tonight's webinar in further detail. So if you had any questions, or if you just wanted to learn a little bit more and you just wanted to speak with your fellow amateur astronomers about this topic, you can join us for our Cosmic Conversations. And this is in partnership with the Museum Educator Alliance as well. So that is next week. It is February 4th, 5 p.m. Pacific, 8 p.m. Eastern. You can have the registration link here in the chat. It is available to all NSN members. And Brian, it's back to you.
All right, thank you very much. So for those of you on Zoom, you can find the chat window and the Q&A window at the bottom edge of the Zoom window on your desktop. Please feel free to greet each other in the chat window, making sure that you select everyone so that we can all see your greeting. If you have any technical difficulties, please put that in the chat, or you can send us an email at nightskyinfo@astrosociety.org. If you have a question for Dr. Seiffert this evening, please type it into the Q&A window. That really helps us to keep track of your questions and whether or not we've answered them or not. So please put those in there. And Vivian, if you could hit the record button for me, please. Again, welcome to the January NASA Night Sky Network webinar. This evening, we welcome Dr. Michael Seiffert from the Jet Propulsion Laboratory. Dr. Seiffert has worked as a research scientist at JPL for the last 25 years and currently serves as the project scientist for the NASA contribution to Euclid. And you're going to see a lot of things from the European Space Agency on here, and so it's a collaborative mission with the ESA and NASA. So Dr. Seiffert's research interests include developing new astronomical instruments and using them to learn about our universe. So please welcome Dr. Michael Seiffert.
Hi everyone. I'll start sharing my screen now. Okay. Well, I hope that's coming through for everybody. Hello, everyone. I'm Michael Seiffert. Thank you for that nice introduction, everyone, and especially Brian. I'm going to tell you a little bit about the Euclid mission today and our journey to try to map the dark universe, as we call it, focusing on the properties of dark matter and dark energy. I'll tell you about the mission and show you some of the early images from the mission. We're still quite early in the lifetime of the mission. But before I jump into those details, I'm going to give you a little bit of background information. There's been a long history of wondering about the universe, wondering what it's made out of. What is the content of the universe? Is it infinite? What is the structure? What is the geometry? And of course, these questions span all civilizations, but I'll just pick out Western civilization. And an early example of that wondering is from the Greek philosopher Plato, who in his famous book, The Timaeus, proposed that the universe was composed of 5 elements that I have shown here. And of course, our modern view is quite different than that, but it sort of begs the question, how do we learn about what's in our universe? Rather than using pure reason as Plato attempted to do, we try to make measurements and learn about the universe that way. In addition to just looking around our neighborhood, seeing what's on Earth here, we can train some of our powerful telescopes at the distant universe and try to learn about what the universe is made out of by looking at some of the deepest pictures that we can gather. This is an image from the Hubble Space Telescope, now at least a decade old. One thing that you can immediately see in this image are a number of galaxies. So I'll just try to point them with my cursor here, and then remember to move the cursor out of the way. You can see those galaxies. Lots of galaxies in this image. In fact, this is a cluster of galaxies. Each of those galaxies has a large number of stars. Many of those stars, we believe, also have planets based on other measurements. But some of the things that are in the universe are a little bit more difficult to see and don't readily show up in visible light. So for example, the Chandra X-ray telescope lets us know that in addition to the galaxies that we see here, there's also some gas that is glowing. And this is a very thin gas, and it's glowing, and it's not just red hot or white hot, it's X-ray hot. The gas is so thin that we can't see it in the visible light with HST, with the Hubble Space Telescope. But with the Chandra X-ray telescope, we can measure the X-rays coming from this region. And we can tell that there's this thin, very hot gas here. And that leads us to the next puzzle, which is, well, this gas is so hot that normally it would just fly apart under its own heat. But it's being held together by gravity. It's being held into the middle of this cluster of galaxies by gravity. And if we just add up all of the mass that we know from all of the galaxies here by counting how big each galaxy is, how many stars it's likely to have, add up all the mass that's there, that's not enough gravity to hold all of that gas in. And in fact, that's one of the pieces of evidence for something that we call dark matter. Dark matter is a substance that many people believe is a fundamental physics particle that's not yet been detected in the laboratory, that permeates space, and it doesn't interact with light or through the electricity or magnetism, but does have gravitational properties. If there's enough of it, it could hold that hot X-ray gas in. There's two other pieces of evidence that you can see in this. We can actually measure the velocities of the galaxies in this cluster, and they're zooming around the center of mass of this system with a certain speed, and we can tell that there would need to be a certain amount of mass here to hold those galaxies from all flying apart. So how much mass would it take to keep the galaxies from all flying apart? Well, it turns out to be more mass than you can get by just counting up the galaxies here. So that's a second piece of evidence for what we're calling dark matter. A third piece of evidence comes from some of the
Looks like Michael froze for just a moment there.
gravitational lensing, where the mass of this cluster of galaxies actually magnifies and distorts the images of these background galaxies, in this case, making these just spectacular arcs. And using some techniques, we can tell that these galaxies are further away than the cluster of galaxies here. And again, we can calculate how much mass the cluster of galaxies has to have in order to produce this gravitational lensing effect to the extent that we see here. And again, it's just the stars and galaxies that we can see in visible light are not enough to make that up. So that's a third piece of evidence for dark matter, just sort of in this one area. And of course, there's lots and lots of other measurements, many of which you've probably heard of, which leads us to believe in a dark matter scenario in which we can't actually detect the individual particles. So our modern view is that the universe has, maybe over 25% of its density is in this dark matter. The hydrogen and helium gas that leads to the areas of hot glowing gas, but also star forming regions, etc. That's another, sliver of this cosmic pie of what the universe is made of, but it's less than dark matter. Stars are only a small part of that, and of course, planets are less than that. And you and me and everybody on this video tonight are just a tiny, tiny sliver of this whole plot. A big part of this plot I've labeled dark energy. That's now what we believe makes up the greatest fraction of the energy of the universe, and we'll get to that in a little bit. This is our modern view. So some history of getting to that point. Well, we've known for some time that the universe is expanding. This was famously discovered by the astronomer Edwin Hubble, who back in the 1920s in a publication made this plot here on the left. The plot shows on the y-axis velocity of distant galaxies, and on the x-axis how far away they were. So he noticed two things. One thing he noticed was that galaxies are mostly moving away from us. And secondly, the further away from us they are, the faster they were moving. And so this is the origin of the idea that the universe is expanding. Like most of science, astronomy is a cumulative field. So often we tell stories about individual discoveries, but if you probe deeper, you usually find that those discoveries rest on a framework developed by scientists that came before. And in the case of Edwin Hubble, in order to make this plot, he used a type of star called a Cepheid variable. And we'll maybe say a few words about that in a second. But the key property of Cepheid variable stars that Edwin Hubble used to make this plot was discovered more than a decade earlier than that by Henrietta Leavitt in some of her work in computing some of the properties of observations made with a different telescope. The data that Edwin Hubble used came from the Mount Wilson telescope, the 100-inch up there. It's still available for tours if you happen to be in the Los Angeles area. This telescope was threatened by the Eaton fire that ravaged Los Angeles recently, but fortunately, this observatory and telescope had a narrow escape. Fire came close, but the telescope is fine. So to make some of these measurements, in cosmology, we rely on something that we call a standard candle. A standard candle is an object in which we have a good idea of how intrinsically bright it is. If we can compare how intrinsically bright we think it is to how bright it appears to be, we can derive the distance. So here's a picture of two candles. This is from my living room. And the candles are pretty similar or standard, but the one that's closer is brighter. And so you can use this as a way of figuring out how far things are away from us. Velocities, and if I can refer back a couple of slides, that plot from Edwin Hubble had both velocity and distance on it. The distance we get from standard candles. Velocities are determined from spectra. A spectrum is the result of passing light from a source through a dispersing element, or in some cases, reflecting off of a dispersing element. And in the lower left, you can see this is a white light entering from the left and going through a prism and being spread into the color of the rainbow, colors of the rainbow. That's what I mean by through a dispersing element. And those of you who are of a certain age, as I am, may recognize this as the album cover from Pink Floyd's Dark Side of the Moon. A modern spectrograph has more detailed information, maybe higher spectral resolving power or higher sensitivity or other features. On the y-axis here is the intensity of light, and on the x-axis is wavelength. And so we can take the light from a star or from a galaxy, run it through our spectrograph, and get one of these curves. And there are a number of features in the spectra that are due to the different elements in the atmospheres of stars or in the gas in between stars that allow us to characterize that particular galaxy. This is a typical galaxy spectrum from the Sloan Digital Sky Survey. And we can use the position in wavelength of those features to learn something about the velocity of the galaxy. So time hasn't stood still since Edwin Hubble's early measurements. We've kept on going. That plot that I showed you to begin with is just this tiny little blue square on this scale. And we've now included other objects. So instead of just Cepheid variable stars to estimate the distance to a galaxy, we use different types of supernova, other techniques, etc. And this extends the range of which we can do these kinds of measurements. A type of standard candle that has become particularly important is a supernova, and a particular type of a supernova called a supernova 1A. A supernova is a star that's exploded. A 1A is a particular history of the star leading up to that explosion. And they can be seen at great distances. They're transitory, so you have to be lucky or persistent in seeing them. But they can be very useful at measuring distances and velocities out to greater and greater distances. As they were measured out to larger distances, a departure from a simple expansion model was evident. And the astonishing interpretation of that is that the expansion of the universe is accelerating. In the lower right here is a picture of Saul Perlmutter, one of three people, along with Brian Schmidt and Adam Rees, were awarded the 2011 Nobel Prize in Physics for the discovery of the fact that the expansion of the universe appears to be accelerating. The plot that I'm showing here is an example of some of the supernova data. The data points here are individual supernova. The solid line, maybe you can see just kind of running through all of this, that's a universe, that's a model of the universe where the expansion is accelerating. And the dashed line is a model of the universe where the universe's expansion is not accelerating. And you might be a little skeptical, I guess, of whether these data points follow the solid line better than they do the dashed line. In fact, they do. It was reasonably significant in a statistical sense. But what was really convincing was a number of other measurements and independent analysis and other observations of things different than supernova that all kind of came to the same conclusion about parts of this that people eventually found convincing. And so the universe's expansion is accelerating. So what is causing the acceleration? Again, an astonishing answer. It appears that there's an extra component to the universe that's repulsive. It tends to drive things apart. And we've given that phenomenon a name. We call it dark energy. We're very ignorant about what it is. There's a few things that we think we know. Point one is that it's approximately smooth. In other words, the amount of accelerated expansion doesn't seem to be particular to one direction in space. It acts like a repulsive force. It's pushing things apart to make the expansion of the universe speed up or accelerate. A very good question that we do not yet know the answer to is whether there's an additional component to the universe, an extra kind of substance or field or particle or who knows what. Is there an extra component, or is our understanding of gravity, and by that I mean Einstein's theory of general relativity, maybe it's that theory of gravity that's incorrect or at least incomplete. And so between these possibilities, I think we don't know the answer. The physicist Michael Turner has said our main achievement in understanding dark energy is to give it a name, and I think there's some truth to that. So since we don't know very much about it, how can we learn more? What is the next step to try to make progress here? Well, the first thing you might think of is, can we measure dark energy in the laboratory? Is there an experiment that we can do? Here's Dr. Bunsen Honeydew giving Beaker a electrical plug to try to measure something. Unfortunately, this does not look very promising. Dark energy is a very weak effect locally, but it's everywhere. And it's really through the vastness of space that it adds up to be enough to make the universe's expansion accelerate. And it's really only on the very largest distance scales that we can even detect its effect. And that's why Edwin Hubble didn't immediately see this when he did his measurements back in the 1920s. It took until the early 2000s before we had convincing evidence of this. Because we can see it through the vastness of space, it's natural to turn to astronomical techniques rather than laboratory techniques to try to learn more about it. So here are the three premier ways to measure dark energy. There's probably a dozen other ways that I could talk about, but for various reasons, these three are the ones that are thought to have the most promise for being precise and not being confused by confounding effects of either modeling or observations or some other issue. Supernova, we've already talked about. They act as a standard candle, and you just look at ones that are further and further away and try to build up your statistics of how many you've seen and how far away they are. They are a little tricky though, because you can't count on them always being there when you point your telescope in a certain direction, and they are sort of intrinsically messy. It was a great way to discover dark energy, and they'll still be used in the future. They'll have an important role, but the Euclid mission and other observations are focusing less on supernova and more on the following two techniques. The first of which is called weak gravitational lensing. So gravitational lensing, like I showed on that, I think third plot of the presentation today, that's the distortion of the shapes of distant galaxies that happens by the intervening dark matter. So dark matter magnifies and distorts the shapes, and you can use that property, and I'll describe that a bit more in a second. And the third premier way is using something that we call galaxy clustering. This is using the statistical distribution of galaxies on very large scales. And I'll also say a few words about that in a second. So let's start with gravitational lensing. So this is an image from Euclid, from one of Euclid's early observations. This is strong lensing. Gravitational lensing comes in two flavors, so-called strong lensing and so-called weak lensing. This is an image of strong lensing of distant galaxies by the mass of a foreground cluster. And strong lensing is usually characterized by very distorted shapes of galaxies, like this one here. You can see some other distorted images on arcs from galaxies. And in some cases, there will be multiple images of background galaxies. So the lens is so strong, it splits the background galaxy image into multiple parts, some of which will be observable and some of which may be more difficult to see. That's the characteristic of strong lensing. Weak lensing is a much weaker effect that's present only in, or that's present everywhere, but doesn't lead to this dramatic distortion of the images. Strong lensing is great, but it's really particular to these very massive clusters of galaxies. So you can learn about dark matter in that cluster of galaxies, but it's hard to use it to learn about dark matter distributed uh, across the universe. And so we turn to this other technique, weak lensing, where we have just a subtle distortion of the background images. It's really only detectable statistically. So here's how that works. So we take some observations of distant galaxies. We can't, for weak gravitational lensing, we can't see the distortion of any one galaxy directly because it's too subtle. But using statistical techniques, we can tell whether a region that we're observing has had all of the shapes distorted in a characteristic way. Um, and then attribute how much of that there is to intervening dark matter. And we can do that at a series of different distances away from us. And again, here, we're using distance in the universe as sort of a time machine. Things that are further away are further back in time. Light takes time to travel to us. So when we look at things further away, we're looking at them as they were, in this case, billions of years ago. We use the weak lensing technique to measure how clumpy dark matter is at different epochs of the universe. So we divide the universe into different slices at different times. We try to measure how clumpy the universe is, and then we see how that clumpiness changes with time. And why does that tell us anything? Well, the clumpiness of dark matter is driven by the attractive force of gravity, which tends to make those clumpy regions more clumpy with time, and the repulsive nature of dark energy, which tends to slow that process down. So how that clumpiness evolves over time depends both on the amount and the nature of dark matter and dark energy. So that's one technique that Euclid uses and that is one of the premier techniques today. Another very important technique I call galaxy clustering. So on the right here is a map of the positions of nearby galaxies. This is a map made with a Sloan Digital Sky Survey. So a couple of things about this picture. We, the observer, are in the middle, at the center of this picture. And as we go out towards the perimeter, we're going further away in distance. This is just a two-dimensional slice. It's not the full three-dimensional picture, but angle along one direction is shown along the perimeter here. And it's this kind of funny wedge shape because this is not a measurement of the full sky. It's just a measurement of particular regions. So a big wedge here and another big wedge on the lower part here, and not so much in the direction of the center of our galaxy. So one thing that you might notice from looking at this picture is that it looks a little foamy or like there's filaments or something. And the interpretation here is that regions that in the early universe were a little bit denser. Over time, through the attractive force of gravity, they became more dense, and regions that were initially less dense became even less dense later on. And that leads to this sort of foamy filamentary structure. And of course, how that happens over time depends on how much dark matter there is. That's doing a lot of the attractive force of gravity part, and also the properties of dark energy, which again are trying to slow that process down. The map that you see here only extends back to about 2 billion years in the past. If you go further back in time by looking at further distances, the structure would look a little different. And by comparing how that looks, how that evolves over time using statistical techniques, we can start constraining the properties of dark matter and dark energy. We make the measurements and we compare them with our models of how such things should be developing over time, either through simulations or analytic theory. And the comparison tells us what's going on. The older generation of instruments, like the Hubble Space Telescope and the Sloan Digital Sky Survey, which I just talked about, those instruments were limited either in how far back they can see, how sensitive they are, or how much sky they can cover at one time. In the case of Hubble, it can only cover a small region of sky at a time. In the case of the Sloan Digital Sky Survey, it had difficulty seeing back at higher and higher distances. In order to make progress on understanding the properties of dark matter and dark energy, we want to measure a larger part of the sky to larger distances. That will give us more regions of space to compare to one another, gives us better statistics and better limits on understanding dark matter and dark energy. So the Euclid mission was specifically designed to make those measurements. And so what do I mean by that? Well, to start off with, these blue squares that I show here at the right, that's the field of view of Euclid with just, you point the telescope in one direction and you take an image, that's the size on the sky that you get. The moon there is just a size for reference. So with one picture from Euclid, you get something that's larger than the size of the full moon. By comparison, the Hubble Space Telescope is just that little square, little black square there, much smaller. And so if you want to measure a large fraction of sky, a third of the sky as Euclid is doing, you really need that large field of view. It's the things that Euclid can measure, it can measure 100 times faster than the Hubble Space Telescope can for a similar large field of view. Hubble is still great if you want to get the very fine detail of your favorite object. But if you want to measure billions of objects, you need something with a wider field of view. So this is the computer rendering of what Euclid looks like. Euclid is currently operating, and it is out at the Earth-Sun second Lagrange point. That's a point in space away from Earth in the direction away from the Sun, about 1.5 million kilometers, a little less than 1 million miles away, in a similar location as the James Webb Space Telescope. So first of all, why is it called Euclid? Here's a portrait painted by Raphael. This is a famous painting, the School of Athens, painted in the early 1500s. And this is meant to depict all of the famous Greek philosophers. And in the middle, you can see here's Plato, here just to the left of center, and just to the right is Aristotle. And if we zoomed in really closely, we could see that Plato is carrying a copy of his book, the Timaeus, in which he proposed 5 elements making up the universe. But that's not why I'm showing you this picture. I'm showing you this picture because over here on the lower right is Euclid. And I'll zoom in on him. So that's Euclid. Euclid was an ancient Greek mathematician, one of the founders of geometry. And this part of the painting is meant to show Euclid instructing geometry to his students and disciples. So that's Euclid. And the European Space Agency decided to name this mission Euclid because the mission was meant to further our understanding of geometry, not in the abstract mathematical sense, but actually measuring the geometry of the universe. How are these clusters and how is dark matter warping space so that we magnify these images of distant galaxies? So that in a nutshell is why it's called Euclid. So back to reality and apart from the art history lesson, here's a picture of Euclid of what the physical telescope looked like shortly before launch. Euclid is a survey telescope led by the European Space Agency. There's a large consortium of scientists working on the project. At last count, over 1,000 scientists working on this. And it also has contributions from NASA, which is why I'm talking to you about it today. Euclid is the first space mission dedicated to the study of dark energy, and we're excited about what we're going to learn from it. In this picture here, this white barrel, that's a barrel that's surrounding the telescope. The solar panel, you can't see, it's just facing directly to the right along this vertical edge. This gold color thing is shielding from the sun. More about that in a few seconds. And this black thing over here on the right is the fairing of the spacecraft. That's the part of fairing of the rocket. This is the part where the whole Euclid telescope spacecraft gets loaded into this fairing and then put on top of the rocket. So Euclid was launched in July of 2023 on a SpaceX Falcon 9 rocket. This is a picture of the launch. Went off beautifully, went into orbit perfectly. And the early observations were really thrilling in that we got immediate feedback that things were working reasonably well. So the primary science of Euclid is to try to gather more sky to higher depth than previous ground-based or space-based missions. And it does that by measuring a large fraction of the sky. And the idea here is that Euclid takes one picture, a nice large field of view, and then it steps over and takes another picture, steps over and takes another picture, and it keeps on doing that for 6 years. So that's the idea of the survey. Just it's going to cover a third of the sky, one step at a time. Euclid has been it had a commissioning period where between July of 2023 and February of last year, there were a number of things happened that it took to kind of tune this up to start working. But it's working well now, and we're coming up on its 1-year anniversary of the start of the survey. Since I know there are some amateur astronomers here, I thought I would just go into the details of the telescope and instrument a little bit. The Euclid telescope is a 1.2 meter diameter telescope. It's made with silicon carbide, which is great for thermal stability and low weight. And unlike maybe a Cassegrain telescope that you might be familiar with, this is a 3-mirror design called a Korsch anastigmat. And the idea here is that it's a specific design that's very useful for producing very good image quality across a wide field of view. And so that's what you need to do to get this, or that's one of the things you need to do to get this large field of view. The other thing that you need to do is have instruments that can accommodate that large field of view with a large array of detectors. So I'm going to show that to you in a second. Euclid has 2 instruments. There's a visible instrument called VIS, which is basically a visible light camera. And there's a near-infrared instrument that is both takes images and also takes spectra. And the light comes from the telescope, from the primary and secondary mirrors, bounces off a couple of mirrors onto a third focusing mirror. Then the infrared light goes into the near-infrared instrument, and the visible light takes a few more bounces and goes into the visible instrument. The visible instrument is a massive array of detectors, so 36 detectors. Each detector is a charged couple device detector with over 16 million pixels. So altogether, 600 megapixels. That's about 150 times more pixels than the most recent iPhone, and a very fine scale of 0.1 arc seconds per pixel. The detectors are operated at a very cold temperature to minimize the added noise to the system. And there's sophisticated electronics to read everything out and send the data to the spacecraft. So this is an image of what all that looks like. There's a plastic cover on top of everything, so you can't quite see the detectors, and that's to protect them during ground testing, this is a picture from. The near-infrared instrument has 16 detectors. Each detector is not a CCD. It's something called a mercury-cadmium telluride array. This is a combination of elements to make the detector sensitive to infrared light. Regular CCD camera is not sensitive to infrared light particularly. So this is the way to do that. It's very similar to the detectors on the James Webb Space Telescope. Each detector, again, has over 4 million pixels in this one. You can't really see the detectors in this picture. You can see the back of them, and I'm going to try to point to the back of the detectors with my cursor here. And then each detector is coupled with this ribbon cable. You can see several of them here. The ribbon cable connects them to some sophisticated readout electronics, which operates the detector, digitizes its signal, and sends it to the spacecraft for further processing before the data is sent to the ground. Not shown here is a filter wheel that has a number of different filters in it, and including a couple of spectral modes. And again, the detectors are operated at a very cold temperature to minimize added noise. This picture is near and dear to my heart because these are the elements that were provided by NASA to the mission. And a bunch of us, both at JPL and also at the Goddard Space Flight Center in Maryland, worked quite hard on this for a number of years to make sure that this was operating as well as could be. Well, it's not all smooth sailing for us. We had some difficulties at the beginning, and I thought maybe it would be interesting for you to hear about some of the difficulties, not just the triumphs. One of the issues that we had early on was stray light. Ideally, we would just see the light from the stars and galaxies that we're looking at, but in fact, there was a glint where light from the sun bounced off of a part of the spacecraft, did a couple bounces, and entered into the instrument cavity and contaminated some of the images. And that's on the left here is an image of one of the images that was contaminated by this stray light. That took some time to debug, but by doing a number of measurements, we were able to figure out which specific orientations led to this bit of extra unanticipated stray light. We modified the operation strategy and re-optimized things. There was a slight penalty to the overall survey efficiency, but we now have ways of restricting the pointing of the telescope so that we don't encounter this problem. So that's an issue that was solved. Another issue that we encountered was solar flares led to solar X-rays contaminating some of our images. If you've paid attention to the sun in the past year, you may know that there have been there's been a lot of solar activity and a lot of solar flares. Of course, we knew about that ahead of time, but for some reason, the shielding around the visible instrument was not quite as robust as we'd hoped. And so when there are very strong solar flares, there is a big blammo that happens on the focal plane, and you see this sort of red color is an indication of the number of additional counts that we're getting from solar X-rays, not from the distant universe. So we can't really stop this, but we have a great way of identifying when a pixel in the camera is being affected by this, and we can remove it from further data analysis. So this will cost us a few percent additional loss of science, but everything can still proceed as anticipated. A third issue, and one of the ones that really had us concerned at the beginning, was some of the guiding and some of the tracking of the telescope. In order to make very crisp images where we're trying to measure these very precise shapes of distant galaxies, you need to have excellent tracking with the spacecraft. And that's done through something called the Fine Guidance System, which uses a couple of sensors that track stars and give updates to the spacecraft to tell it where to point. There was some software issues where when we were looking at a region that had particularly few stars in it, the guidance software would get confused, and it would sometimes think a cosmic ray was a star. And that would send the software to tell the spacecraft to move when it shouldn't be. And there were some software, there were some automated rejection algorithms to prevent that, but they didn't work as expected. So the European Space Agency and one of its industrial contractors spent 4 to 6 months working on this problem, redeveloped new software, tested it on the ground, uploaded it to the spacecraft in flight, and now things are working really well. So that was a problem that could have been very serious, but was solved with some hard work and solved successfully. And that's led to some of the pictures I'm going to show you here. These are the Euclid early release observations. These are the first science images from Euclid and highlight its capability. They're not meant to do the primary science of the properties of dark matter and dark energy. There are other things that you can do with a telescope that you designed for dark matter and dark energy, and some of them are quite spectacular. I'd like to mention that the data is publicly available. Here's the link to the website. And a number of amateur astronomers have downloaded the data and processed it on their own using different contrast or different color scales to process and make beautiful images with. And so if you're interested in that, please go ahead. The early release observations represent about 24 hours of observing time compared to the 6-year lifetime of the mission. And I'll mention just a couple of these. This is the Perseus cluster of galaxies. So one thing that you can do with Euclid data that's not the primary science of the mission is to try to understand the properties of dwarf galaxies. These are galaxies that are much smaller than your typical galaxy. They are not a big part of the total mass or the total brightness of a cluster of galaxies, but they are very numerous. And so this image has, I think, around 100,000 dwarf galaxies in it. And by studying them, you can learn about the formation and evolution of clusters of galaxies and galaxies themselves. Another spectacular image here is of the Horsehead Nebula region. This is an image of that region with a star cluster near the top, which is thought to be a promising region for searching for objects that are smaller than a regular star, often called substellar objects or free-floating planets. And there's been a long-standing question about whether, if you plot the number of stars versus a given mass, whether that's a smooth function or whether there's features in it. By looking for things that are smaller than a regular star, we can start answering some of those questions. Euclid is a great telescope to find those sorts of things, though to really follow them up, you'd want to use something more powerful like the Hubble or James Webb Space Telescopes. So now I'm going to jump into a little video here. This is a video from ESA, and I'll pause for a few things along the way. This is a view of of the full sky. I'm just going to pause it here. Okay, so the sky is not shaped like an egg. This is a projection of the sky onto this oval shape, much as you might see a globe unrolled and displayed in 2 dimensions. The region in orange are regions of particularly low galactic dust or other contaminants. They're regions that are very good for observing the distant universe. So those regions in orange are the areas of sky that Euclid is going to cover. The central line through this picture is the plane of our own galaxy. The center of our galaxy is in the middle of this. Some objects from the southern hemisphere, the large and small Magellanic Clouds are visible here. But Euclid is going to measure this orange region, and this video is going to highlight 1% of the Euclid survey, which is going to be shown here just in a second. So that's this region in the lower right here. So that's 1% of the full 6-year survey that's now been completed. And we're just going to zoom in and take a look at what that looks like. So we're going to zoom in again. This is all real Euclid data. This is no simulations or anything like that. One of the characteristics about Euclid that's really just amazing is its ability to cover a wide region, but also maintain the just fantastic level of detail and depth. This video sort of highlights that. pause here just for a second to sort of point out that in addition to this big spiral galaxy, all of these little guys around the edges, these are all galaxies too. So just a ton of stuff going on in every part of every Euclid image. Now that we've seen this, we're going to zoom out again just to sort of put this back into perspective of what's going on. So that's 1% of Euclid, and that's a nice video made by the European Space Agency. So I'll just wrap up here. The expansion of the universe is governed by the presence of dark matter and energy. The expansion is accelerating, and we don't know why. Euclid will test some of the fundamental ideas of our understanding of gravity and of Einstein's theory of general relativity with some of these fantastic new measurements. And this will be an exciting journey, I think. And I'll just end there. Thank you, everyone.
All right. Thank you very much, Michael. So we've got some really great questions, and so let's get right to them. Very early on, Sherwood asked a question: what suggestions have been made to account for dark matter other than some kind of invisible matter?
So great question. So some people have postulated fundamental particles. Some people have postulated primordial black holes. Some people have postulated modifications to the laws of gravity, such that they're different on large scales than what we measure in the solar system. Some people have suggested new types of fields. So instead of an electromagnetic field, there's some other field that's modifying gravity. Generally, the possibilities fall into two categories: a new type of fundamental particle or a new modification of gravity.
All right, and kind of staying with the idea of this, so Arturo asked, and this is back onto slide 1, do the three pieces of evidence for dark matter agree on the amount of dark matter?
Roughly they do, but I, for one, would not be convinced if it was just down to those three pieces. Tons and tons of different pieces of evidence come together, from rotation curves of galaxies on relatively small scales to something called the cosmic microwave background, radio waves left over from the Big Bang, to clusters of galaxies. The fact that we get roughly the same answer from widely different measurements, I think, is the thing that's convinced most people in the field that this is a real phenomenon.
Thank you. And Anna noted that on one of them, I think it was one of the pie charts early on about the distribution of matter and energy. From one of your diagrams, it seems that the total mass of neutrinos is comparable with the total mass of stars.
I think maybe my plot was not super accurate on that point. The neutrinos are a smaller part, I think. Neutrinos are very light and they have a little bit of mass. I think in stars, we have more like a few percent, and I think neutrinos are a fraction of that.
And Jeff asked this question, and as we look deeper into space, we are looking backward in time. So if more distant objects are moving away faster, then doesn't that imply a deceleration with time?
I think, let's see, this is maybe a little hard to picture, but imagine you have some two-dimensional graph paper, and we're sitting at one of the intersections of lines on that graph paper, and now we're just going to stretch that graph paper. The little squares that are nearby you are moving away from you, but as you stretch that graph paper, you'll see that the parts of those intersections that are further away from you will be moving away from your little intersection. It'll be looking like they're moving away faster. But now, instead of stretching that graph paper at a constant rate, imagine accelerating the rate that you use, that you're stretching that paper. So I think we had expansion for a while. We were expecting the universe's expansion to slow down and decelerate, but instead it's accelerating, and that's the puzzling part.
Yeah, I think that's a tough question. And, if we had some props here, I think that it would be
Yeah.
much easier to think about.
I could dedicate a whole topic or whole 3 hours just on that one topic and never actually get to pictures from Euclid. So
Yeah, so that was a tough one. Thanks for that. Stuart asks, is dark energy and or dark matter homogeneous, or is it detected in clumps, kind of like the web structures of galaxies that we know?
yeah, so dark matter is very much clumpy, and that's our evidence that regular matter to some extent follows the clumpiness of dark matter. Dark energy we think is smooth, though I can't say that our observations are great at this point. The current thinking is that it's a smooth component to the universe for dark energy. Dark matter is clumpy, like in the sense that regular matter is as well.
Okay. And I'm sorry, I'm not going to pronounce your name right. Manjunath asked, was dark energy known during Hubble's time? He's read,
No,
that,
it was
he read that the universe is expanding way too fast to fit any theories, including Hubble's theory and the constant. Is this due to the discovery of dark energy?
so Edwin Hubble definitely did not know about dark energy. And in fact, his early measurements of the expansion of the universe, although it showed the expansion of the universe, the actual calibration of his measurements were off by a factor of 5. So we've made a lot of progress since those days. I think we're down at trying to do things at the 1% level, not at the factor of 5 level.
All right, I think we have time for a couple of more questions here. We had a question from Cliff about one of the diagrams that you had showed some black lines, vertical and horizontal through there, and was asking if it looks like data is missing in the dark strips. And is this filled in by dithering? And I'm not sure what dithering is, but maybe you do.
Oh yeah, so some of those pictures of the field of view of Euclid, the detectors don't line up right against each other. There's a little gap in between the detectors. And we try to minimize those gaps, but if you took a picture of the sky, you would have gaps in it. And so for each region that Euclid observes, before it moves on to the next region, it makes a series of 4 little steps, or 3 little steps to have 4 different positions. That's frequently called dithering, where we move the telescope a small amount and take another picture of essentially the same region just to fill in those gaps that are in between detectors. And of course, the detectors are not perfect. Some of them have a few broken pixels, etc. And so moving the telescope in between exposures like that also helps fill in those things.
All right, we're going to do one more question here. And so this will be the last one. So I'll apologize in advance for the ones whose questions weren't answered. So Zachary asks, is dark energy postulated to be a constant force, or is it becoming more repulsive as the universe ages?
I think the question to that is, we don't know. I think the simplest explanation is that it's an additional constant that's in Einstein's equation of general relativity, but we have to admit that we really don't know the answer to that question. I think we hope in the next decade or so to start answering those sorts of questions with more precision.
I think the best answer to that is that that's why we're launching missions like Euclid, is to hopefully start having a glimmer of an answer for these things. There's so many things that we don't know and may never know, at least given our current technology.
Absolutely.
Yeah. So if you want to go ahead and stop sharing,
Sure.
that'd be great. So.
Okay.
Okay, well, thank you, everyone. Kat's going to put in a link to the survey into the chat here in just a moment. That's all for tonight. Join us next week for an edition of Cosmic Conversations on Tuesday, February 4th at 5 p.m. Pacific Time. And I believe Kat already put the registration link for that into the chat. Our next webinar is on Tuesday, February 25, when we welcome Joseph De Pasquale, who will bring us up to date on what JWST is observing and discovering. And so, we kind of have all of these different webinars about all these different missions, and it's interesting how they all can actually work together to have a more complete image or understanding of what's going on with the universe. And earlier, before the webinar, I had asked Michael about whether Euclid was going to work hand in hand with the wide field of the Vera Rubin telescope. And do you want to make just a quick comment about that?
Yeah, I will say, some of the advances that we expect in the future will come directly from combining data from different missions. We can do better by combining data from the Rubin telescope, from the Roman Space Telescope that NASA will launch later on this decade, and also from observatories on the ground and from observations at different wavelengths. It's really a golden age of just incredible astronomical facilities, and we have to use them to the very best extent we can.
All right. Well, thank you so much, Michael, for joining us this evening. And thank you, everyone, for tuning in. You can find this webinar, along with many others, on the Night Sky Network YouTube channel. So keep looking up. We'll see you next week for Cosmic Conversations, and in about 4 weeks for the next webinar. So good night, everyone.
Thanks, everyone.
Good night.
All right. Well, thank you so much. This is great.
Sure.
I love that we had so many people too, and I think I counted something about in the mid 170s on here. Of course, some of the